In this lesson, we'll continue our study of homomorphisms. And to get us started, here's our opening task. We have the set U13 containing 12 elements 1 through 12. And our task is to divide this set into 4 equal-sized subsets with 3 elements each. So for instance, here's one way to do it. We can go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, 12. Now, it turns out that this isn't a correct answer. And you might be surprised to hear that there is a correct answer, at least from an abstract algebra point of view. So let me erase this answer. And now, if you could pause the video and see if you can come up with a way to divide this set into 4 equal-sized subsets with 3 elements each. And now, please pause the video and work on day 18 classwork. Afterwards, we'll go over some of the problems and concepts. In today's classwork, we studied the function lambda from U13 to U13, where lambda of a is equal to a cubed for all inputs a. And here's a visual representation of that lambda, which happens to be a homomorphism. Now, in this picture, we've arranged the elements in the domain U13 according to the elements in the codomain to which they map. So 1, 3, 9, those are bunched together because those 3 elements all map to 1 in the codomain. Likewise for 2, 5, 6, they all map to 8. 4, 10, 12 map to the same element, namely 12. And 7, 8, 1 all map to 5. And so right in front of us, we actually see the answer to our opening question. This homomorphism lambda, in fact, divided this set U13, the domain, into 4 equal-sized subsets with 3 elements each. So here's the observation that I'll make. A group homomorphism partitions the domain into equal-sized subsets. Now, when we say partition, what we mean is that these 4 subsets do not overlap at all, and they cover all of U13. So that's what we mean by partition. It turns out, and I'll leave it for you to think about, any function does the partitioning. It subdivides the domain into non-overlapping sets that cover all of the domain. So the fact that lambda partitions the domain, U13, that's not a big deal. What is a big deal is that those subsets are equal-sized. It's not that we have 4 elements here, 2 there, 1 there, and 5 there. They all have the same size with 3 elements. And so that's a special property about a group homomorphism. And we'll see why that happens in not too distant future. Now let's talk about the codomain U13. Not all elements of the codomain are shown here. There are 12 elements in U13, but only 4 of the elements, those that were hit by the function lambda, are being shown. And so let me just go ahead and fill in the rest of the elements in order to emphasize that codomain can contain elements that aren't hit by our function. And so here is 1 is already hit by the function, but 2 isn't. Neither is 3. 4, 5 did get hit by the function, but 6 didn't. 7 did not either. 8 was hit by the function, but 9 was not. Let's see, there's a space for 10. And down here for 11. And then 12 did get hit by the function. And so now we can cross off this comment. In fact, all elements of the codomain are shown in our picture. I'd like to highlight one more thing about this figure, and it's the 3 elements 1 through 9, which I'll put in a subset of the domain U13. Now these elements are special because they all map to a very special element in the codomain, namely the identity element. And so this subset 1 through 9 is called the kernel of the homomorphism lambda. The kernel contains the elements of the domain that map to the identity of the codomain. And we'll say more about the kernel in general in the next slide. Now let's generalize and define what we mean by the kernel of a homomorphism. So let theta from G to H be a group homomorphism. Then we define this set, elements A and G, such that theta of A is equal to the identity of the codomain. So this is a subset of the domain G containing elements in the domain that map to the identity element of the codomain. This set is called the kernel of theta, and we typically denote it as ker theta. So here is a visual of the kernel. We have a homomorphism theta from domain G here to codomain H. And here's kernel K. Elements A and B, for instance, are in the kernel because they both map to the identity element of the codomain. Whereas this element X is not in the kernel because it maps to something other than the identity element of the codomain. Now we've seen in the classwork through examples the following theorem. The kernel K is a subgroup of the domain G. And so we'll prove this in the next slide, but let's discuss a plan for it. And so in order to show that K is a subgroup, we need to show closure. Associativity comes for free because the operation is inherited from G. And we also have to show identity and inverses. And so what do we mean by that? Well, if elements A and B are in the kernel, we need to show that their product. We know it lives in G because G is a group and G is closed, but we need to show that the product is in the kernel. So we want A times G, A times B rather, to be in K. And I left a little space there to denote the fact that we're multiplying them inside G. So we're using the operation of G. We also need to show the identity element is in the kernel. So we don't want the identity element to be somewhere out here. We wanted it to be in here. And let's call that epsilon G. So that's what we need to show. And last but not least, the inverses. So if A is an arbitrary element of the kernel, we need to show that A inverse, again, we know A inverse exists because everything is happening inside a G, which is already known to be a group, but we want A inverse to live inside the kernel. So those are the 3 elements we'll show that are in the kernel. And that's what we'll do in the next slide. Now we'll prove that the kernel of a homomorphism is a subgroup of the domain G. And just as a reminder, to say that an element is in the kernel means that it maps to the identity element of the codomain. So let's keep that in mind. So we'll start the subgroup proof. Now remember that a subgroup proof is essentially I think of it as 3 mini proofs: the closure, the identity, and inverses. And so let's start with closure. So we'll let A and B be elements of the kernel. And we have to show that their product is in the kernel as well. But what does it mean that they're in the kernel? Well, they both map to the identity element of the codomain. So then theta of A is equal to the identity of H, and theta of B is also equal to the identity of H. Now we need to show that A times B in the kernel is in the kernel, so we need to show that A times B gets mapped to the identity element of the codomain. So let's go ahead and do that. We're going to use the operation preserving property of theta. So let's start by writing that. Since theta is operation preserving, we have theta of A times B, where the multiplication takes place in G, is equal to theta of A times theta of B, where the multiplication takes place in H. But we know that theta of A and theta of B are both equal to the identity. And that multiplication still takes place in H, but an identity times identity is certainly equal to the identity. And so what we just showed is that theta of A times B is equal to the identity of codomain, which tells us that A times B is in the kernel. Thus, A times B is in the kernel, so that K is closed. Next, let's show that the identity element of G, namely epsilon G, is in the kernel. In other words, we need to show that epsilon G satisfies this property. So let's apply theta to epsilon G. Well, we know we get epsilon H because theta, being a homomorphism, preserves the identity. So let's write that down. Since theta preserves the identity, we have theta of epsilon G is equal to epsilon H, and thus epsilon G is in the kernel. And last but not least, inverses. So given an arbitrary element of the kernel, say A, we need to show A inverse is also in the kernel. So let's apply theta to A inverse and see what happens. So finally, we have theta of A inverse. Now we showed last time that this is equal to the inverse of theta of A. So this is the inverse of theta of A. But we know that theta of A is equal to the identity. So this is equal to the inverse of the identity element of H, but the inverse of the identity element is just the identity itself. So we just showed that theta of A inverse is equal to the identity element, which tells us that A inverse is also in the kernel. And so we can put a bow onto this proof and say, hence, K is a subgroup of G. And that's the end of our proof. Let's return to our homomorphism lambda. Now we just showed that given any homomorphism, its kernel is a subgroup of the domain. In the example of lambda, the kernel happens to be the subset containing 139, and we showed in the classwork by building its group table that 139 do in fact form a subgroup of U13. Next, we'll describe another important subgroup that's associated with a homomorphism. We'll put our focus on the codomain of lambda and highlight the elements of the codomain that are actually hit by the function lambda. So 1, 8, 12, and 5. Together, those elements form a subset of the codomain called the image of lambda. And we see that the image doesn't equal all of U13, and that's another way of saying that lambda is not onto. Now it turns out that the image happens to be a subgroup of the codomain. This is true in the case of lambda, which we saw by building a group table of 1, 8, 12, and 5 in the classwork, but it's true in general. Given any homomorphism, its image is a subgroup of the codomain. And for the proof of that claim, please take a look at the chapter 18 reading. But for now, that's the end of today's lesson, and I will see you next time.